Welcome back. In this lecture, we introduce a new approach to the problem of similitude. This is known as the scale factor approach. The learning outcome of this lecture would be using the scale factor approach to obtain modeling and prediction rules. This approach is far more general and powerful than those discussed earlier. Unlike the process involving non-dimensionalization of the governing equations and boundary conditions, this approach does not require a mathematical model, and that is a lot of saving. And unlike dimensional analysis, which operates in a relative vacuum of any physical model, it gives some insight into the physical model. Not the whole insight, but some insight. And therefore is amenable to reasoned relaxation of the modeling rules. One of the problem of using any similitude approach is there are too many similarity rules, and we cannot tailor our materials to make all those similarity rules applicable. And so some relaxations have to be made. The scale factor approach permits us to make reasoned relaxation of modeling rules. We'll come to this towards the end of the course. We start with introducing the concept of scale factors. We first introduce geometric similarity and geometric scale factors. Consider two scaled models which are geometrically similar. Let's call the larger one the prototype and the smaller one the model. A model does not need to be always smaller than the prototype. But for discussion today, let's assume that the smaller is the model and the larger is the prototype. A geometrically similar model is one in which all the corresponding dimensions in the model and prototype bear the same ratio. Thus, the geometrical similarity requires that the ratios of all corresponding dimensions in the prototype and model are equal. If R denotes the radius of the nose of the body, then Rp by Rm, the radius in the prototype divided by radius in the model, is equal to the chord Cp of the prototype divided by the chord of the model. Each of these ratios being equal to K sub L. K sub L is read as the length scale factor. So, scale factor is equal to the value of a parameter in the prototype divided by the value in the corresponding model. Let us consider two areas, one in the prototype and the other in the model, the scaled model. Then the area of this area is equal to del xp multiplied by del yp, the length in the x direction of the prototype multiplied by length in the y direction. Similarly, area of the model would be del xm multiplied by del ym, the two areas. And the ratio of these two would give us the area scale factor Ka. Clearly, this is equal to Kl square. The geometric similarity ensures that the scale factor for the area would be the scale factor for the length squared. Similarly, the scale factor for the volumes Kv would be Kl cubed. All volumes in the prototype and all volumes in the model, the ratios would be Kl cube, a unique factor. We introduce here the concept of homologous points again. We have talked about that. The 2 points AP in the prototype and AM in the model are termed as homologous points if the ratios of the x coordinates is equal to the ratio of their y coordinates, both being equal to KL. These points are known as homologous points. So, from one point in the prototype, we can determine the corresponding location for the homologous point in the model. This will play an important role in later discussion. Concept of similarity implies that the same holds for each of the other quantifiable quantities, that is parameters and variables, both dependent and independent, such as velocity, time, stress, force, power, work done, etc. Each and every quantity imaginable. This is to say that value of any quantity at a point in the prototype is related to the value of the same quantity at the homologous point in the model through the corresponding scale factor. There is a unique scale factor for a unique quantity. There would be a velocity scale factor, a time scale factor, a stress scale factor, a force scale factor, etc. Let's talk of velocity similarity. On the same body, at 3 points 0, 1 and 2. In the prototype, we have 3 velocities as shown: V0p, V1p and V2p. We consider the model and we consider the homologous points in this model corresponding to 0, 1 and 2. These are the homologous points. Let the velocity there be V0m, V1m and V2m. Then the similarity of the two requires that the ratios of the corresponding velocities in the prototype and model is identically the same. There is a unique scale factor for velocity Kv, and the ratios of the velocities at homologous points is identical to Kv, whichever point we talk about. This is velocity similarity. Further, it is just not the magnitude of velocity that are so related, but the direction of the velocity at homologous points must also be the same, as shown in these two pictures. One a prototype and one the other a model. The velocities V1, V2 and V3 in the prototype and the model have exactly the same directions. It should be clear that this would require that the individual components of velocities are also scaled by the same scale factor Kv. Thus, the horizontal velocity component u1 at the prototype divided by u1m for the model is equal to the vertical velocity v1p for the prototype divided by v1m for the model, both being equal to kv, which was the ratios of the velocity v1 for the prototype divided by v1 for the model. And the same kv, the same ratio would hold for 0.2 or 0.3 or any other point in the two fields. The geometrically similar prototypes and models are said to have kinematic similarity if all the kinematic quantities, including the velocity, such as frequency f, the RPM n, the angular velocity omega, acceleration alpha, angular acceleration alpha, volumetric flow rate q dot, etc., have constant scale factors. Different scale factor for each quantity, but for that quantity, a constant value at any pair of homologous points. The basic strategy in obtaining these similarity rules consists of exploiting the fact that the scale factors for various quantities are not all independent. It is all right to say that the scale factors should be constant. But what makes the scale factor constant? That is the problem. And as discussed earlier, we need modeling rules for the purpose. We choose the uniquity parameters of the model such that they satisfy the similarity requirements. But what are those similarity requirements? The similarity rules. And here we state that the basic strategy in obtaining these similarity rules consists of exploiting the fact that scale factors for various quantities are not all independent. Like we have seen, the scale factor for area Ka is equal to KL square. Ka and KL are not independent. Similarly, the scale factor for volume was seen to be KL cubed, not independent. The interrelationship between these various scale factors are converted into relation between independent parameters for the prototype and model. Some of these would involve the independent parameters, and they would be related to the independent parameters of the prototype. So these will give the relations between independent parameters, the uniquity parameters of model and the prototype. The remaining part of this lecture and the next lecture would be devoted to how those rules are established. For example, let's start with the scale factor for velocity, Kv. It must be related to scale factor Kl and Kt of length and time interval respectively. Kv, the scale factor of velocity, is equal to V prototype divided by V of model at the homologous point. V of prototype can be written as dxp, the distance travelled in the prototype, in time dtp divided by dxm, the distance travelled in the model, divided by dtm. This is written as dxp over dxm into dtm by dtp. This is nothing but the length scale factor KL, and this is the reciprocal of the time scale factor KT. Time scale factor KT is defined as TP divided by TM. time in the prototype divided by time in the model. So that we obtain the relation Kv is equal to Kl and Kt. These three scale factors are not independent of one another. Kv into Kt divided by Kl is equal to 1. Now, Kv is Vcp by Vcm. Kt is Tcp by Tcm divided by Kl, which is Lcp by Lcm. And that should be 1. By rearranging, we get Vc Tc by Lc for the prototype is equal to Vc Tc by Lc for the model. Subscript C denotes that this is a characteristic value. Whatever characterizes the velocity, time interval and length in the prototype, the corresponding value in the model must be related to these through this relation. Vc Tc by Lc is then called a pi number. It is dimensionless. It would be dimensionless the way we have constructed it. The characteristic value of the velocity times the characteristic value of the time interval divided by the characteristic value of the length would have the same value in the prototype as in the model. So, this is invariant. And that is why it is termed a pi number. This is just starting on the road to establish modeling rules. Ensuring similarity consists of obtaining scaling relationships for the values of the independent parameters, of the uniquity parameters, so that given the values of the uniquity parameters for the prototype, we can determine the values required for the model for the similarity of the phenomena, for ensuring that the two things, the prototype and model, have similar behavior. Once the similarity between the prototype and model is achieved by the proper choice of the independent uniquity parameters, it can be shown that the dependent quantities would also have constant scale factors. This leads us to prediction rules. If we do similar exercises as we did for the velocity, we would determine this collection of the scale factors of the various kinematic quantities. For time, the scale factor is Kt, and we have written the scale factors in terms of two sets, Kl and Kt in this column and Kl and Kv in this column. Usually in fluid mechanics, length and velocities are preferred uniquity parameters. So, the second column is quite useful in fluid mechanics problem. Elsewhere, Kl and Kt may be used. For velocity, we have just determined that Kv is equal to Kl divided by Kt in terms of Kl and Kt. Of course, in terms of Kl and Kv, it will simply be Kv. Angular speed, frequency RPM, the scale factors for these quantities, K omega, Kf, and Kn, would be 1 over Kt per unit time. And this would be Kv by Kl in the second formulation. Similarly, for acceleration, rate of change of velocity with time. Velocity is Kl by Kt, so acceleration is Kl by Kt squared. And in terms of Kl and Kv, it is Kv square by Kl. Most frequently used in fluid mechanics. Angular acceleration, similarly, can be written as 1 over Kt squared. Velocity gradient, K of dv by dt is 1 over Kt or Kv by Kl. Volume flow rate, Kq dot, is like scale factor of volume, which is Kl cubed divided by scale factor of time. So Kl cubed by Kt. Or it can be used as area of cross section times the velocity. So scale factor of area is Kl square and that of velocity is Kv. You do not need to remember these because they can be obtained in no time whenever you require them. Pi numbers. Given one example for the velocity, let's give one more example. Let's obtain a pi number involving the volume flow rate, Q dot. Volume that passes through in 1 second, in 1 unit time. So scale factor for Kq dot, we just obtained in the last table that Kq dot can be written in terms of Kl and Kv as Kl square divided by Kv. The another formulation was Kl cubed divided by Kt. But Kq dot is equal to Kl square. Kv implies that the ratio of the volume flow rate in prototype and model is equal to the square of the ratio of lengths multiplied by the ratios of the velocities in the prototype and model respectively. And from this, by rearranging, we get Q dot divided by L square V for the prototype must be equal to Q dot divided by L square V for the model. The characteristic nature of these quantities involved is understood. We do not write sub C all the time. It is understood that each of these quantities carried the subscript C, that it is a characteristic quantity, a Q dot that represents the flow, a length that represents the problem situation, a velocity that represents the flow situation, or that is typical of the problem involved. So Q dot divided by L square V is a pi number whose value must be the same in model and the prototype. This may be used as a modeling rule if all the three quantities Q dot, L and V are independent, but if one of them is a dependent, this would be the prediction rule. We'll come to this a little later. So, after obtaining the scale factors that we did earlier, and these are contained in these two columns, we convert them into pi numbers. These pi numbers represents the non-dimensional groups of parameters which would have identical values in the prototype and the model. The characteristic nature of the quantities contained herein is understood. Now let's come to dynamic similarity or the interrelationship between scale factors for dynamic quantities. The prototype and the scale model are said to have dynamic similarity if the net forces at homologous points in the two are related by a constant scale factors Kf. F for force. So Kf is a scale factor for force. However, the force at a point in a system is related to kinematic quantities. Newton's law of motion relates the net force F on an element to its acceleration A and its inertia. So if Kf, Km, and Ka are the scale factors for forces, masses, and accelerations respectively, we can write force is equal to ma gives us Kf, the force scale factor would be Km times Ka. And as we have converted the relationship between scale factors to a pi number, we can obtain F by Ma is a pi number. So value of F by Ma is the same in the prototype as in the model if the phenomena is similar. One way to easily organize these relationships is to construct a flow diagram like this. Kf, the inertial force, so we put a subscript I. Inertial force is one that involves acceleration. So scale factor for inertial force is like scale factor of mass times the scale factor for acceleration. Now the scale factor for mass is written from mass is equal to density times the volume. So Km is like K rho KL cubed. And Ka on the other hand, we obtained earlier is like Kv square by Kl. And this gives a relation Kfi is equal to K rho Kv square Kl square. This is one formulation of the scale factor for inertial forces in terms of the three quantities K rho, Kv, and Kl. If we wanted to use Kt, this would have a different formulation. The preferred formulation in fluid mechanics is this. But you will obtain similar results if you use the other formulation. You may not recognize the relation immediately, but you will obtain very similar relations. And this relation between scale factors would give you a pi number. Fi, the inertial force characteristic, divided by the density times the characteristic velocity square, divided by characteristic length squared, are identical in the prototype and the model. Once we did for force, we could do for other dynamic quantities like momentum P, the torque T, work done W, the power, work per unit time W dot, the pressure P, the shear stress tau. These columns list the scale factors in terms of K rho, KL, and KT in the first column, and K rho, KL, and KV in the second column. Similar to what was done for the kinematic quantities earlier. And the resultant pi numbers are given in this part. These are just for illustration purposes. We don't need to remember them. We'll obtain them as we do the problems because it takes almost no time to obtain these pi numbers. The question that needs to be answered now is how to obtain modeling rules that will ensure full similarity between the behavior of a prototype and its geometrically similar model. This requires specification of the values of the uniquity parameters, that is, of the independent parameters for the model flow given their values for the prototype flow if we are dealing with fluid mechanics. Similarly, for other sciences, solid mechanics, heat transfer, or any other science. One approach follows from the recognition that the total force acting on a fluid element which results in its acceleration is the vector sum of the various forces, namely the pressure forces, gravity forces, and the viscous forces, etc. There may be other forces involved, surface tension force, compressibility force. But we have listed the typical forces in simple problems. Similarity requires that not only the total forces on the prototype and the model elements be scaled by a unique scale factor, which depends on the scale factors for mass and acceleration, but the same factor must scale every component force that make up the total force vectorially. So it is not just the inertial force, but the viscous force, the pressure force, and the gravity force. They also must be scaled by the same scale factor Kf. So if this was the total force, which was made up as a sum of three component forces added vectorially, the pressure force, viscous force, and the gravity force. If this was the picture in prototype, then the picture in the model should be same. The direction of each component must be same, and the magnitude for each of the component forces should be modeled by the same scale factor Kf. This is the crux of the argument that we use for obtaining modeling rules. So it's not only the total force that must be scaled by a constant scale factor Kf, each component must be scaled by the same scale factor Kf. So the process of obtaining modeling rules consists of identifying the various force components that determine the net force at a point in the flow field, obtain the scale factor of each of these force components using the physical laws that govern the phenomena. The third step, equate the scale factor so obtained to the net force scale factor Kf obtained from the Newton's law of inertia. And this scale factor is termed as the inertial force factor. Then obtaining the non-dimensional pi numbers in terms of the characteristic independent quantities from the relationships established in step 3 above. These gives invariant that establish the modeling rules. Example, let's obtain scale factor for viscous forces. Viscous shear forces would be shear stresses times the area. Shear stresses are obtained from the Newton's law of viscosity. Tau is equal to mu times the velocity gradient dv by dy. So the scale factor for shear stresses would be scale factors for viscosity times the scale factor of velocity divided by scale factors for the length. Scale factors for area is easily written as Ka is equal to KL square. So, the scale factor for the shear force, which we denote by Kf, comma mu, is nothing but K mu, Kv, Kl. This gives you a pi number F mu divided by mu Vl. The scale factor for viscous forces divided by the characteristic value of the viscosity, the velocity and length should be same in the prototype and in the model. We can do this for each of the forces. We already obtained the inertial force factor Fi, and from this we would obtain the pi number Fi divided by rho L square V square. The scale factor for unsteady forces is obtained from the law that unsteady forces is mass times the unsteady acceleration, del V by del T. For mass, we use K rho into KL cubed. Del V by del T is KV by KT. And so the resultant pi number is this. For viscous forces, we obtained the pi numbers as F mu by mu LV in the last slide. Similarly, we could write for gravity. The gravity force is mass times g, and mass is density times the volume, so that Fg divided by rho gl cubed is the pi number for the gravity force. Similarly, for the pressure force, Fp divided by delta P, the pressure difference, into L square for area. Similarly, for surface tension force, where the law is the surface tension force is sigma times L. For compressibility, where the law is the E times the area. And for the centrifugal force, where the law is mass times omega square R. This is the list of pi numbers so obtained. We will learn to use them in the next lecture. Thank you very much.